our group and program works on developing all kinds of really cool marine science toys to enable some great work. So we're going to talk a little bit about that today. First, I'd like to begin by acknowledging traditional owners of the lands in which we're all joining around the world. For us in Hobart, it's the Muyanina people, and we pay respects to their elders past, present, and emerging. A very brief context to CSIRO. CSIRO is the government research agency for Australia, and unlike many other countries, Australia has one civilian agency that does the majority of its fundamental research. So it's a very large organization approaching 6,000 researchers and scientists across 52 sites in Australia and spanning a large portfolio of work from genetics to farming to mining to ocean science. CSIRO also has a very strong track record of collaborations with industry, and I won't go through all the things, but many of you right now might be joining this call over Wi-Fi, and Wi-Fi was one of the seminal inventions of CSIRO many years back, amongst others. So chances are that you've interacted with some CSIRO technology in your lifetime, which is always really exciting. I'm part of what's called the National Collections and Marine Infrastructure Program, which comprises of a number of components, the Atlas of Living Australia and the National Marine Collections, which are collections of animals, fish and wildlife, insects, and so on. That's managed and curated by the CSIRO. Engineering and Technology Program, which is the program that I'm part of. We have this Environomics group and also Marine National Facility, which is our research vessel operators. Within our engineering and technology program, we have a technology roadmap, which helps guide the type of research that we're interested in. These are the primary 7 categories. We're going to talk a little bit today about this autonomous systems, touching a little bit on some of the others. A little bit of context, we're talking today about polar challenges, of course, but the work that I'm going to be focusing on is some of the work we're doing in the Southern Ocean, although we do have some collaborations with our colleagues up north, but a lot of the challenges that we face, I think, will be reflected in some of the work happening up north. So the Southern Ocean is where we're going to be today, and here's a shot I took earlier in June, actually, down at roughly 57 south of Australia. So let's just give you a sense of the great expanse that we're dealing with. So when I get up every morning, this is what I think about. This is the problem that faces us all every day, which is here we have the Australian continent, as you can see, surrounded by a giant, big blue ocean. The ocean we're trying to monitor and trying to address goes all the way from the tropics down to the marginal ice zones, goes from shallow water all the way to deep water. It goes from calm conditions to really rough conditions. It goes from no current to really high current. So we have all the regimes you can imagine contained within this geographic region around Australia. And so we wake up every morning trying to provide technologies and methods to support the type of science observations necessary to answer key questions for the Australian public, primarily around things like climate change variability and also environmental impacts and remediation, all these great things. The Southern Ocean, as you can imagine, is a very challenging place. Here's some examples of some of the conditions that we're facing. This is from one of our mooring sites, a Southern Ocean Flux series. It's an air-sea flux mooring that's combined with some oceanographic sensors. You can see here in the top right, sort of a corner map of Australia, the 2 red dots. That lower red dot is where that mooring is taken. So not even in the Southern Ocean, just barely in the what we call the subantarctic zone. Not even in the polar front zone or even in the Antarctic zone. And so you can see here plots of a histogram of wave height and also wave period. And so you can see we have wave heights recorded in excess of 16 meters at the site with a nominal wave height of greater than 6 meters. And these are typical conditions, and wave periods of around 10 or 12 seconds, but can extend quite further. So there's a lot of very open water, which prevents a lot of engineering challenges for us to try and solve. And again, looking at wind speed, we're talking about a mean wind speed of at least 10 meters per second, which is 20 knots. But of course, gusting much higher than that. We've had wind gusts recorded at our soft sites in excess of 70 knots. And so, again, very dynamic site. This gives you an idea of what you can expect. The top right is sort of like the nominal conditions on the back deck. quite a lot of green water they having to deal with. And so this is what we call a calm day. This video here on the left. Can I get a thumbs up, Natalie? Is this coming through? Can you see it? Oh, that's awesome. That's great. So again, this video was taken this past June in the Southern Ocean. Again, these are sort of good conditions, what we call good conditions, but really challenging. The second challenge that we face, particularly when we talk about the Southern Ocean, is access. Getting to the Southern Ocean is very hard when you can get there at all, and particularly getting there in times like winter is extremely difficult. The best opportunities that we have to measure Southern Ocean properties are using the ECOP program, which is the panel in the top right. And this shows you a snapshot of the current state of the Argo flows from July 2023. So you can see this reasonable distribution, but we still have many gaps. You can see north of the Ross Sea, there's quite a few gaps, and there's some gaps south of Australia. But these are, of course, profiling once every 10 days, and they don't give us all the information we need to really understand what's happening in the marginal seas and what the changes are going on. The center plot here shows you some ship tracks from the last 10 years. And so despite having some ship access, particularly resupply vessels and commercial fishing vessels operating in the Southern Ocean on a regular basis, we still don't see a lot of coverage from research vessels in the majority of the Southern Ocean. So access is a huge problem. We don't have as many ships, we don't have as many opportunities to take measurements as we'd like. The panel in the bottom left shows particularly how the challenge is particularly acute in Australia. So the blue bars there are showing the marine estate domain against all the countries. Australia is the third plot, so it's the third largest marine domain in the world. And the orange bars show commissioned scientific research vessels, and you can see Australia at a measly 2. And we say 2, but it's really sort of 1.5 because one of our research vessels is actually Antarctic resupply. So the number of research vessels that Australia has to combat the observing challenge is extremely small. And so we have to be extremely creative on how we solve this. The other thing that's a bit challenging about the Southern Ocean is we have to span a whole lot of science domains. Everything from the physical oceanography, the top sort of center, understanding the currents and circumpolar exchanges of water. You may have heard recently about the weakening of the Atlantic currents. All these currents in the ocean basins all meet and exchange in the Southern Ocean. And so the Southern Ocean is has a very important circulation and a very important contributor to how water masses get exchanged in the other basins. And so trying to understand that is really important. Trying to understand the nature of ice and the ice breakup and the subsequent biota and biome that happens in the Southern Ocean and near the ice edge. And of course, all the other things that come with the terrestrial monitoring on Antarctica itself. So there's a whole range of science domains we're trying to observe and trying to understand, and we have challenges in observing all of them. Before we get into some examples, I just want to sort of set the scene and talk a little bit about some of the trends that we're seeing in global observing that help guide our decision making when we pick little platforms. A lot of these trends, I had written a paper coming out of the OceanObs 2019 decadal planning process, and I think a lot of these trends still hold true a number of years later. And that is, for example, in infrastructure, we're seeing shifts from monolithic infrastructure investments to distributed infrastructure investments, which improve resiliency and redundancy and provide more flexibility of operation. In sensing, we've gone 20 years ago from single modal observations to multimodal observations, incorporating more science observations in a single platform or a single sensor. Planning is increasingly probabilistic rather than deterministic. This is a little bit of a slow trend, but we're seeing changes happening in that space. In the data in particular, this is an interesting one. We've really changed in the last 20 years from delivering raw data, so delivering, say, a common CSV file or an Excel file or an etcdf file, just raw data points, to actually delivering data products. So to helping climb the value chain of data and provide data products and tools to help scientists and decision makers actually extract value from the data we're getting. And this is really because we still have a big data problem. Even though we're data poor in terms of observations, we still have a big data problem in terms of the science pipelines. And so transitioning away from raw data to data products is really important. And on the operational side, we see that increasingly partnerships are increasingly important in order to succeed, particularly with some of the technology developments we're talking about. So moving from lead agency models to consortium models and team models. And I'm going to give an example of that today in one of the case studies. Underlying all these trends are a number of fallout effects that we need to contend with, things like interoperability, the increased reliance on technology, the introduction of new business models and how science interacts with industry and how we get technologies out into the mass market, how we deliver technology at scale, and how we work together between industry, defense, and civilian research to deliver great outcomes for everyone. So when we think about, particularly in autonomy, which I'm going to talk a bit about today, when we think about those trends and we think about the problems and challenges that we're facing in the Southern Ocean, what we end up with is that platforms, science platforms that we use are increasingly becoming autonomous. Sensors are increasingly becoming integrated and platform optimized. And really the goal is to develop technologies to enable and enhance autonomy within sensors and within platforms and networks to help deliver observational solutions for the science community. Now, what is driving all these changes? We talked about the global trends, talked about some of the challenges. What's driving a lot of this? There's a few things. The first is demand. We have a huge need right now for observations in the Southern Ocean and at the poles, because that's where we see the most drastic changes in relation to climate change and climate variability. So the demand for this data is greater than it's ever been. There's increasing pressure, particularly from government state agencies, to be flexible and adaptable in how you make observations, to be able to respond to events, whether they're near-term events or long-term events. The complexity of the observations is increasing. So we talked about going from single modality to multimodality. So gone are the voyages where you just go out and do CTDs for 40 days. Now you're expected to do a whole lot more. And that leads to this question of ROI. So increasingly, particularly when we talk about government investment, global government investment in ocean observations, it's basically been flat for the last 20 years and arguably decreasing when you index to inflation. And so increasingly, those of us in research are being asked to deliver more observations for less money. So the return on investment, there's a huge amount of pressure to do more with less, and it's extremely challenging when we talk about getting funding and resources to kind of enable the science that we're dealing with. These drivers are manifest in a few particular challenges, especially when we talk about polar regions, which is this issue of localization, persistence, and scale. Localization means the ability to make observations, to be at the right place at the right time. Persistence, to be there as long as you need to be there to answer your science questions. And scale, meaning to be able to do it with diminishing costs. Okay, so be able to find techniques and approaches that allow you to increase your observations at diminishing costs. And so underlying all of this, which is the thesis of today's talk, and hopefully I will convince you in the next 45 minutes, is that autonomy is the future of ocean operations. Not just ocean science operations, but all ocean operations, blue economy operations, oil and gas operations, defense operations, biosecurity, you name it. If you're doing something in the ocean, autonomy is the key enabling technology that's going to help meet the challenges of the future. Not manned research vessels, not anything else. So this is our thesis. This is something that we've been extolling for the last 10 years and investing heavily in some key components to help make that future a reality. Not that those other things aren't important, but we feel autonomy is key. When we look at the technology maturity of autonomous systems, here on the left, I have some of the science domains which we work on: physical oceanography, hydrography, acoustic studies, and so on. And on the bottom axis, I have the technology readiness levels. And so you can see when we look at the science domains and we think about how we can leverage sensing and how that intersects with autonomy, we see that this spans a whole range of technology readiness levels. Some things like physical oceanography sensing is quite advanced in the autonomous space, brought to us in a great part by the Argo program, but also by other initiatives. And so there's a lot of mature work in that space. Still more to do, which we can talk about a bit later. Whereas other areas, for example, ocean chemistry is still a maturing and growing area of need of research and development investment. In particular, one thing I'll point out is that regulatory maturity at a global stage is still extremely young. It still has a lot way to go. Some countries, in particular the United Kingdom, have extremely advanced and detailed regulations around the use and handling of autonomous platforms, but other countries have nothing, and some are always in between. So there's a huge spectrum in terms of regulatory environment that we need to consider when we're delivering these technologies to the forum. And so we always encourage people, when we're talking about autonomy, to also bring regulators into the conversation. That's a really important part of developing a good partnership and for success. So a lot of exciting work to do. What are some of these enabling areas that we might think about for the next, say, 10 or 20 years? Sensor intelligence is a big one. So we talk about embedded AI, edge computing, the introduction of more intelligent decision-making on sensor and on platform. And there's a lot of people, of course, as we know, working on this. One of the most important things when we talk about the increased use of sensor intelligence is having integrated chains of custody. So chain of custody of data is extremely important. To be able to take any observation and trace it back through the sensor, through the configuration, through its entire life cycle, through every calibration, through every maintenance period, and to be able to have a gold standard of traceability between the data observation you're making and the physical product that's being delivered. This is a really important thing, and we're actually working a lot on this thing as well. There's a little bit in here around security as well, and tamper-proof and all these other things. And in 10 or 20 years, I think it's going to be a particular challenge as we start to see more autonomous platforms being used to deliver data. There's a lot of work in sensor hardware. We talk about miniaturization a lot. There's an umpteen number of low-cost projects in the world trying to do things, trying to produce a more large variety of sensors that are not necessarily gold standard, but that can deliver data in particular scenarios. We think that's really exciting. And of course, we're seeing a lot of next generation, optical, low Earth orbit satellite, and also LiDAR and laser-based sensing. There's a lot of really cool stuff happening there. And then, of course, systems. And so we're going to talk a little bit later about some autonomous surface vehicles. And so the proliferation of systems in the last few years has skyrocketed, and we expect in the next 10 or 20 years that innovation will continue, and hopefully within the next decade sort of plateau to some subset of mature platforms. So I'm going to present two case studies today that are going to help give you some idea of the kinds of challenges that we face and the kinds of solutions that we at CSIRO have been working on. One is around biomass assessment. So how do we conduct biomass assessment in these large ocean basins, particularly the Southern Ocean being a large ocean basin, a large basin for primary productivity of the oceans. And another one about how do we tie in air-sea flux, ocean carbon, and physical oceanography observations on an autonomous platform. I think I'll just keep talking through this. If you have questions, please make note of them. And I'm happy to go back through the slides and answer your questions later on. All right, so today I'm going to talk about this one platform, which is a family tree, if you will, called the acoustic and optical system family. And in particular, I'm going to tell you a little bit about this one platform here and this family tree called the profiling acoustic and optical system. So where does this family tree begin? Well, it begins with our old school fisheries scientists here in the top left, who would go out to sea and put nets in the water and collect all kinds of critters and produce what I would call an analog histogram. You can see here on the right, this is what I call an analog histogram. They take a net, catch a bunch of critters, lay them out like this, photograph them, measure them, size and weight, and all of this, and produce a distribution. And then using the magic of statistics, wave their arms a little bit and then say, well, based on this study, we think the ocean basin has X and X gigatons of prime productivity. This is the biomass assessment. And for many, many years and decades, this is how the work was done. And at CSIRO, we, of course, worked with the scientists to develop all kinds of different contraptions to try and make that analog histogram better and to stratify it more. So in the old days, they would take a single net and tow it through the water and come it back. And then you had all these issues of net avoidance and, of course, integration, because you're towing the net from shallow water to deep water to shallow water. And so you're basically integrating the entire catch through that entire cycle. And so one of the technologies that we developed was this open and closing net system to help stratify the observations. In other words, to help have net tows that are discrete at different depths so that you don't have the integration problem, so that you can have depth stratified histograms. So that's great. But that still relies on a big ship, and it still relies on you going to sea and counting all these things and measuring them by hand and doing all this. So it's very time consuming. So enter acoustic technology from ships. And you might not realize, but there's a lot of fishing activity that goes on in the Southern Ocean in particular. And so we had these partnerships with some of the fishing companies to introduce acoustics and install acoustics on their vessels, and they would go out and we'd get this. What you can see here is an echogram. Sort of the red contour you can see here is sort of the seafloor, and these sort of bluish green spots are actually fish. And in this case, we see likely orange roughy. So we'd use this and we'd get some backscatter signals, and it'd give us some idea of where the biota in the water column is living. But it's hard to know, it's hard to quantify this at the moment. It's very sort of qualitative. And so we said, well, we need to quantify it. We need to understand what these target strength signals are and how they relate to actual biomass. And so we went and we designed this towed body system, which would take the echo sounders and tow them very close to the fish schools, very close to the biota, so we can get very detailed echograms of specific targets. And so this is an example of a 38 and 120 kilohertz system. And so instead of that big fuzzy blob, you can see little targets. And these little targets, each one of those is an individual fish. Okay, so then you can go back to that same seamount, you can do a survey, and you can pick out individual fish from the fish school, and you can count them. You still don't know how big the fish are necessarily, but there's a way to do that. And so what we then do is create something like this. We install this system. It's called our acoustic and optical system. We install it on a trawl net, on the headline of a trawl net. And what it contains is a whole package of bioacoustic transducers, which sonify the catch of the trawl in real time, in situ, as it's being caught in the net, and also take photos of it, stereo photos and video of the catch. And this is an example of an image you might get from one of these nets. So these are orange roughy being scooped up by the trawl. And so we're sonifying each of these targets acoustically, and we're also taking photos of them and developing some software tools to measure their individual target strength and associate that with their size and length and mass. And so then we can take that blobby image and take those targets and actually do fish catches. So instead of taking the fish and individually measuring them, now we can take we can go on a commercial scale and go to the big fishing vessels, take giant nets, sonify them, and get the histogram almost instantaneously. As soon as the system hits the deck, we've got the histogram. Don't have to do the fish counting and weighing anymore. Waste of time. So now we can do this. So micronecton survey, we're looking at tiny little critters now in the ocean. And so we did a survey here going from Hobart here to the north of New Zealand, across the Tasman Sea, and stopping at a few places along the way and doing these studies. And so then we get something like this. Okay, so you can see the blue and the green are the sort of biota. You can see them going up and down in the water column through their day-night cycles. And you can do this in near real time and get a really good data, really good sense at this cross-section of what the actual biomass is for that transect. And again, using some magical statistics, make some inferences around what the biomass is for the entire basin. That's really exciting stuff. One of the challenges, however, when doing this is you still have to use a trawl. You still have to use a line. You still have to tow something in the water. And so you still have some issues of integration, and you still have some issues of avoidance. In other words, the net comes up and a lot of things swim out of the net. A lot of things are avoided the net because the net produces a bow wave. And a lot of the critters, particularly the really, really small ones, these siphonophores and these micronecton, get destroyed in the net because the net just tears them to shreds. And it is thought that these could make up a huge proportion of biomass. Okay, so what we need to do is get close to these critters without creating this bow wave. And so what we've come up with is this profiling system. So we take that same acoustical package and the same video photo package, and we put it on a giant profiling platform. It's a Lagrangian profiler. You put it off the side of a boat. It's neutrally buoyant. It's got a buoyancy engine, so it can adjust its buoyancy and direction. And it can sit in the water column as if it's a stationary object, and then sonify the water column in peace without disturbing the biota around it. And it can do this autonomously, so we can deploy this for days or weeks at a time in an ocean basin to get a sense of what the actual biota is around it. hopefully give us a better measurement. You can see here the top right view of some of the echo sounders, transducers that we're using on the bottom of the platform. The transducers are looking down. And then we've got a series of cameras looking down and obliquely looking to the sides to take photos and videos of all the different critters. I think there's a little video clip here of it sort of going over the side of the vessel. This is our vessel, RV Investigator, deploying a system off the side there. Pretty cool. And here's a little video of what it looks like when descending slowly in the water column. So there you can see through the video there was some siphonophores. This is just all marine snow, some little critters, and there's a little squid. Really excited. We find animals bump into the system quite often because the system's not moving. It's not moving and it's not emitting light aside from the lights it's emitting, and so it's able to kind of sneak up on things, sneak up on fish schools because it's so slow moving in the water column. It's a pretty cool thing. We have some really great, shots. Here you can see on the right some images of siphonophores, and again, most of the time you would have to conventionally use an ROV, going down, spending many hours at depth with an ROV, going and hunting for these siphonophores to take videos and images of them and sort of count them manually. But we can just deploy the system, and it can take thousands of these images. We find them in spades, and we can collect huge data sets of siphonophores. And the scientists, of course, love it, going through all the identification, sizing, and counting, and everything. And again, with the fish, because we've developed that target strength linkage to the acoustics, we can again sonify fish schools as they swim by, get their histograms, and measure their biomass in situ. And again, you can see another video here of the top left. This bottom left image is kind of cool. This is again an echogram showing individual fish and individual siphonophore targets. So these really tiny little siphonophores coming in and out of the beam. And again, we can measure their target strength and make a biomass estimation over long periods of time. No avoidance problems, no counting fish manually. We can do this now at basin scales. Again, still using the magic of statistics to make an inference around the entire biomass, but now being able to leverage that power of autonomy to really get a really rich data set. And this system, incidentally, now we're working on it to be able to be deployed by non-expert, non-technical teams, so that you can make use of ships of opportunity and also commercial fishing vessels, which might be operating in remote areas. We talked about challenges of access to the Southern Ocean, and being able to deploy a system like this and get some really cool data sets. So some really cool stuff happening. All right, so that was a little story about biomass and how autonomy can really help close the loop on the biomass observational gap. Now we're going to talk about something different, and we're going to start our story not in the Southern Ocean, but in the coastal region of Victoria, in the Bass Strait, and then we'll end in the Southern Ocean, I promise. So this all started, we had a project many years ago to conduct some carbon capture and storage monitoring for some of our stakeholders in the Victorian government. Victoria is one of the states of Australia in the southeast, and they had a lot of coastal oil and gas wells that had been decommissioned that are in the state marine boundary, so very close to shore, maybe 1 or 2 miles from shore. And they had proposals to convert some of these oil and gas wells into sites for pumping in carbon, sort of carbon sequestration, or what we call marine carbon sequestration. Incidentally, this is a big area of focus now around the world. People are looking at how do we capture and store carbon. But one of the big challenges in doing this is you need to understand what the geology looks like in those reservoirs where you're pumping this carbon, and have some sort of observational program that can help you understand when that reservoir fails, and when you see signals of seepage or of changes in the CO2 environment around these wells, whether those are due to leakage or whether those are due to some natural variability that just happens to be at the site. So before going into some trials, we were commissioned to go in and do some studies assessing the background variability of the site to try and understand what a proper and sensible monitoring regime might look like. And so we developed what we call this multimodal survey and planning tool. And we developed a multimodal survey plan to conduct monitoring over the course of 5 years. And the monitoring plan included a whole range of technologies. We developed custom surface moorings, bottom landers, subsurface moorings. We had a whole range of technologies operated from ships. We had divers going out with some really cool tools to do some of the seabed work. And we also had the opportunity to integrate an autonomous surface vehicle. I'm not going to talk about all that other tech. It's really cool stuff. I don't have as many hours as I'd like. But we're going to talk a little bit about just the autonomy piece. The use of an autonomous surface vehicle to augment some of the observations in the context of understanding a carbon sequestration and storage site. So when we think about autonomous systems, there's a number of different platforms, and trying to understand their relative strengths before we get into the details. Conventional is what I call marine, sort of an unmanned vessel. We have unmanned aerial vehicles, we have autonomous underwater vehicles, AUVs, and we have unmanned surface vehicles. I'm working with an IEEE and our colleagues in other technical domains to try and standardize the naming of all these things. And so those of you listening from IEEE in other areas, please reach out. We're really keen to try and see if we can't find a common lexicon to describe these things. So here we have sort of a qualitative measure of what the different sensor payloads, range, endurance, sea surface penetration, and costs are for various systems. And we decided that, you know, if we're going to add autonomy to the mix, having an unmanned surface vehicle is really a good mix between conventional vehicles, but also being able to carry some payload and do some air-sea interaction. So we thought that was a good place for us to sit in this project. And so we did a review. Status of USV technology. A little asterisk here. This is from 2015, so this is extremely dated. But in 2015, this slide represents probably the totality of unmanned surface vehicles available at that time. And some of these, in fact, weren't really available at scale. They were still kind of prototyping. But today, in that intervening number of years, 5, 6 years, 7 years, the landscape's completely changed. And we see today a whole other family of unmanned surface vehicles in the market, and that's extremely exciting. But at the time, this is sort of what we were looked to deal with, and we decided to develop a partnership with Saildrone in San Francisco to help solve some of our problems. So this is the Saildrone. It's a wind-propelled autonomous surface vehicle. It doesn't have any active propulsion, at least not this version. So the wind pushes it through the water. It has a keel, and it has batteries and solar panels to recharge and run all the payloads. It's an extremely simple and robust system, and we were really excited to have an opportunity over the course of 6 years to use this system in a variety of applications. This is the payload that we have on it. So a whole series of what we call subsurface measurements in the oceans, everything from ocean currents, some biogeochemical measurements, sort of chlorophyll, CDOM, and so on, backscatter, dissolved oxygen, PCO2, which is a very special custom system developed with our colleagues at NOAA PMEL in Seattle. Very cool system. We'll talk a little bit about that. The usual water temperature stuff. Atmospheric measurements, which were absolutely key, not only for our Met colleagues, but for understanding air-sea flux measurements. And air-sea flux measurements, that air-sea exchange, is a really important driver for some of the oceanographic models. And in the Southern Ocean, very, very sparse observations. At one point, there were 2 permanent air-sea flux stations in the Southern Ocean. And a number of years ago, the OLI folks canceled the one off Argentina, which is operated by Woods Hole. So at the present time, and for the last number of years, we've only had one single air-sea flux measurement in the entire Southern Ocean operated by CSIRO south of Tasmania. So air-sea flux measurements in the Southern Ocean are gold if you can do them well. So this was really exciting to have this opportunity to try it out. So this was us way back in 2016, whenever it was, 2015, commissioning these systems. We had a long series of work with Saildrone, incorporating the sensors, designing custom interfaces and tools and so on to get the sensors running and calibrated. I think there's a little video of us here in Hobart getting the systems out of the bay. I might just skip ahead here. There we are, sort of pushing the systems along. Getting the wings up. See our research vessel there in the background. And using a crane, getting them in the water. All these vehicles for our deployments were deployed from the dock. So we weren't deploying them at sea, we weren't towing them out, we were deploying them autonomously from the dock, which is a really cool thing to do. Leave it there. We'll talk a bit about it later. So we deployed these systems out of Hobart. And one of the cool things that we did and invested a lot of time in, you can see in this photo in the bottom right, you see that we have a little plate here with some booms. And this was a calibration system that we had developed to help calibrate the acoustics in situ. Again, if you're trying to make in situ biomass assessments using these bioacoustic transducers, it's really important that they're precisely calibrated, not only in the lab, but on platform before you deploy them. And also to understand the dynamics, the physical dynamics of the platform you're using and its bubble profile. So all the subsea hydrodynamics, where bubbles are being swept down, where bubbles are being cavitated and generated, and how the platform is moving relative to the ocean surface. So characterizing and understanding all this and building it into a calibration characterization system for the acoustics was extremely important. And we spent a lot of time kind of working through that with sail drones. That was really great. And so using the sail drones, we went back to this Gippsland site. You can see here in the top left, sort of an ocean map of the site near the beach where we were going to do this profile. The three green squares here are locations of subsea landers, and in between these landers is actually where the well was located. So we were trying to circle that point and measure that whole site. And so this is one of the surveys here. You can see in the center panel, we've sailed at a lake's entrance in this instance, across the beach to the site, operated at the site for something like a month, and then sailed back. And we repeated these surveys a number of times over many years. So some of the data, this is kind of cool. There, top right here, we have fractional CO2 measurements for a period of, this is like a couple weeks. So some really cool data there. We can see a scatter plot on a map here in the center right. And in the bottom, some of the results of the actual data itself. So what's really cool here is we deployed a surface mooring at the site with also a state-of-the-art ocean carbon sensor. And we see there that we have, between the system we had on the sail drone and the system on the mooring, we had a better than 4 ppm agreement in ocean carbon measurements. So that's really exciting. That really demonstrates the ability for us to take conventional ocean carbon measurements, miniaturize them, and run them on a surface vehicle and still get really cool, high-quality data. But what was really important when we looked at the air sea flux information is that on the dry air side, compared to Cape Grim, and Cape Grim is the northwest of Tasmania, not extremely close to this site, but relatively close. And it is one of the gold standard global atmospheric watch sites for measuring atmospheric carbon. It's one of a number of sites in the world. It is one of the gold standards. It's got the cleanest air in the world. And compared to it, we were less than 1 ppm off in the partial pressure of CO2. So that was really exciting. I mean, we were just over the moon to get these kinds of results, which proved two things. One, that you can take gold standard measurements of an autonomous surface vehicle, and that you could then use that for air sea flux information. So that was really exciting for us. On the bottom left here, you can see some of this echogram data again. Now you guys are experts in echograms, so you can tell what all this stuff is. Maybe not. On the right here, you can see there's a fish school being detected, and again, we can sonify the fish school. We can do histogram mass distribution and estimate biomass and so on. But what was really cool here is we were also able to develop some technology to detect bubble plumes. So when we could see the bottom, we can detect bubble plumes, and we can distinguish the bubble plumes from the fish schools. And so we can go across and get some bubble plume information. We can see bubbles seeping from the seabed and measure those, and we can also calibrate the system so we can actually understand the mass flow rate of those bubble plumes. We don't necessarily know what gas is in them from the acoustics alone. You need some chemical sensors to help you with that, but you can detect the plumes in situ. So that was some really cool stuff that we did. But on the back of this air sea flux success and this ocean carbon measurement success, we thought, what else can we do with these systems? And so the natural tendency, whenever we have this idea, said, let's go south. Let's try it. It's a pretty crazy idea. We wanted to go to the Southern Ocean with an unmanned surface vehicle running a full autonomous mission. It never been done before. So 2018. And not only has it never been done before, but we had this great idea. Let's go in wintertime. Why not? There's no vessels in wintertime. Nobody goes down in wintertime. Let's go in wintertime, see what happens. So we worked with Saildrone a lot to try and ruggedize the systems. And so we set south from Hobart in the winter of 2018. Went down to around, I think it's around 57 south. straight south and then hung a right and went into New Zealand, to Bluff, New Zealand. A little short mission, a couple weeks. What you can see here on the right panel is the wind speed, the gusting wind speed on one of the days we were there. So you can see here we've got gusting wind speeds in excess of 50 knots as these storm fronts come through. So that was a pretty challenging set of conditions for our little sail drone, but we made it. We had a bit of damage as we went into Bluff during the recovery phase, but otherwise we did fairly well. And so here's some photos of us kind of putting around. I don't know how many of you have been to sea, particularly in a place like the Southern Ocean or in the Antarctic or the Arctic, sorry. But photos never do it justice. It always looks way more calm in the photos than it does in real life. But these are some of the photos we took, which was pretty cool. And here's some of the extreme situations. Again, towards the end of the deployment, here nearing Buffalo, New Zealand, we were getting wind gusts in excess of close to 40 knots. So that was pretty extreme. And of course, being a wind-powered system, when you get those gusts in excess of 40 knots, the things kind of keeled over quite a bit, but still doing pretty well. So on the back of that success, we thought, what else can we do with this? You know, we've gone into the Southern Ocean, we proved we can survive in the winter. So can we do something a little bit more ambitious? And so working with Saildrone, we came up with this plan, which is the Antarctic circumnavigation plan. So we tried, let's try and see if we can do a lap of the Antarctica. Why not? And we talked with some of the community, and we decided to come along with some primary science objectives. So we said, oh, let's use those bioacoustics to understand a little bit about what's going on with primary productivity. And so I said, well, let's look at krill. Let's see if we can detect some tagged penguins or tagged whales through some hydrophone information. CO2 flux, ocean acidification, met observations, air sea flux. This was sort of the primary for us. And then, of course, the usual kind of whale detection and other things that we're doing. So, but this is really exciting, really ambitious. And like I said in the previous introduction, which is that we're seeing more single agency to consortia as a trend going on. And there was no way Saildrone and CSIRO could do this on their own. And so we brought together a whole consortium of collaborators, most importantly funded by the Li Ka-shing Foundation, to go out and to try this, to put it out there for a year and see what happens. And so we did in 2019. Before we went out, like I said, we had some challenges with those wings in the Southern Ocean. And so Saildrone worked on their design and produced what they call now this hurricane wing, just sort of a square box wing, which not only allows us to navigate in extremely high wind conditions, but allows us to have much higher levels of survivability in excess of 100 knots. And you would likely have seen in the preceding last few years that the NOAA in the United States is regularly sailing this design of Saildrone through hurricanes to collect air sea flux information in hurricanes. So that's pretty exciting. But we did it first with them in the Southern Ocean. This was the wing that we'd come up with, and the sensor payload again, a little slightly reduced sensor payload for this particular mission, because again we're doing all year-round operations and we're concerned about power management and so on. So we kind of focused the payload to that science program that we talked about earlier. So there we go, 2019, we set sail from Bluff, New Zealand, heading east, and 196 days later, returned back to Bluff, New Zealand to complete a circumnavigation of Antarctica. Really exciting stuff, and if you're interested in looking at this data as part of our agreement with the consortium, the data is available for free to download. You can go to data.saildrone.com and look at it yourself, use it, publish whatever you like. Really exciting work. Here's some videos from some select periods, photos from select parts of the voyage. Again, I don't know how much you get from this, but it's pretty cool. Some cool things that we did along the way was try to invest in increasing the level of intelligence and autonomy in this platform. And so there's two things that we did. One is, you can see here on the left-hand side in the Weddell Sea near Argentina, showing the various fishing grounds. And so when we're trying to look at krill abundance and biomass, it was important for us to try and see if we can transect through some of those fishing grounds. And so building that into the algorithm to identify fishing grounds and to try and transect through them. And then on the right-hand side, we worked with our friends at NASA JPL to use their satellite ice products for the Southern Ocean to see if we can't do in situ sea ice avoidance during the missions. And so there was a lot of work with NASA on this. Of course, the satellite products in the Southern Ocean are quite poor because of high cloud cover, and so you don't always get good ocean images, but we worked with them. Unfortunately, we did get stuck in an ice flow. You can see here on the bottom right, just east of Argentina, we got stuck in an ice flow, and we had to do some intervention here. Not physical intervention, but digital intervention through satellite to kind of get it out of the flow and then back on track. So there's still a lot of cool work to be done here in closing the loop between some of these other observations and how autonomous platforms work, but generally worked extremely well. In this panel here, you can see some of the sea ice here in the distance. Again, don't look very impressive from the water line, but pretty exciting to get so close to sea ice. So following the work, okay, sorry. Another cool thing that we did with the platforms is try and do rendezvous. So try and program in rendezvous along the way autonomously. And so one of the rendezvous we did is back to our good old friend, the soft site Airsea Flux Station south of Tasmania, and to do a flyby and to orchestrate a flyby. So we did there, and you can see here some of the comparisons of some of the measurements that we took, and again noting that the CO2 measurement is within better than 1 ppm. What's cool to note here is that by the time we left from Bluff, New Zealand and came all the way around Antarctica back to south of Tasmania, we're around 170 days or so into the mission. So despite that sensor having been deployed 170 days prior on a completely autonomous mission, we were still within 1 ppm measurement of CO2 compared to this Airsea Flux Station. Again, a really exciting sort of outcome there. Subsequently, in 2020, there was a second mission with 2 sail drones. And again, here they were looking at doing rendezvous with SOCOM floats, these Argo floats that have carbon measurements. And you can see them here in a few spots, sort of trying to intersect with the SOCOM path, which is pretty exciting. This mission was cut short due to COVID and a few other reasons, but still really exciting. In the interim, NOAA was extensively using these systems in the Arctic. And in 2019 and late 2019 and 2020, they were deploying these up in the North Chukchi Sea, and in fact went into deep pack ice north of 60 to 65, 66, and so on, further north in the pack ice. So here's some photos of the sail drones actually operating in pack ice. Really exciting. They demonstrated not only their ability to navigate in these conditions, but to have survivability and to collect some really cool science data. So the platform has certainly proven itself with this payload delivering some really great outcomes. So those are some 2 case studies, and we'll take questions in a minute and try and answer some of your really exciting questions. But if you can take something away from this, I'm going to leave you with some of these questions based on these learnings that we've had from these case studies. So the first is, how can we direct infrastructure R&D operational investments between all our collective agencies to better prepare and address future technology challenges faced at our pools? The technology challenges faced at our pools are not dissimilar from those in, say, tropical waters or the open ocean or so on, but they're more acute. So any problem that anyone else has is a lot worse at the pools. So how can we help direct some of that investment to solving specifically the pool problem? Okay, what opportunities do we have collectively to collaborate and work together and get added value not only from new projects, but from existing portfolios? So that's a really interesting one. And this is why I think I really miss going to some of these conferences, particularly the IEEE Oceans Conference, because this provided the opportunity to talk with a whole range of collaborators and really try to find and identify opportunities to work together. Consortia are the future. How do we strengthen our interagency investment approaches in technology to do 2 things? The first is improve interoperability and reduce duplication of design effort. There's nothing that's more frustrating than spending years on a problem and finding out it doesn't work, than to then go to a conference and meet someone who said, hey, we tried that 5 years ago and we found the same thing. And just, oh, geez, it would have been nice if I had known that. I wouldn't have done it. So how can we learn from each other's mistakes? Because the investments that we have to make are so small, we can't afford to be making the same mistakes twice. So how can we work together to improve that? And also interoperability is really important. And so this is something we talk a lot to vendors about and to industry about, saying, can we have common APIs, please? Can we have common interfaces, please? Both physical interfaces and digital interfaces. Because that allows us to chop and change, it allows us to customize, it allows us to send a piece of gear to someone else to use, and they can figure it out. They don't have to do everything from scratch. So how can we work together as a community to address this? And finally, at an agency level, at each of our home institutions, what structural changes can we advocate for to enable new ways of thinking in terms of adaptive approaches to operations? So many of you will come from agencies which have a long history of doing certain things in a certain way, and that may be just fine, and we may be able to do that very effectively and very efficiently and so on. But it doesn't scale, doesn't address those issues of localization, persistence, and scale that we talked about. It doesn't help us address the ROI challenges and the external pressures coming on. And so how can we work with our home institutions to help them think a little bit more laterally about how they make those investments, particularly in the technology space, so that we can help start tackling these other problems? So thanks very much for everything. I'd like to, special thanks, of course, to all of our colleagues on the Profiling AOS team. These are some of them. There's a whole lot more. This work was one panel of a whole family tree of technologies, and there's a lot more that I could have talked about, but this is the particular one that I showed today, so it's really great. And of course, thank you to all of our colleagues on our sail drone project. So this is a photo of us here in San Francisco. You can see me there in the center with Richard and the whole sail drone team at the time. When we took this photo, I think, again, this was probably 2016 or 2017 when we took this photo. This was the sail drone company at the time, was I think 22 people. And I think today there's something like 222 people. So they've really grown by 2 orders of magnitude since we started working with them, and we're really happy that they're finding, success. So thanks very much, and of course, I'm very happy to take your questions.
Thank you very much, Andreas. That was a excellent webinar, really detailed, covered off a lot there as well, so really fantastic. As I said at the outset, folks, if you have any questions, please just raise your hand. There should be a raise hand button at the bottom under reactions for you, and if you raise your hand, I'll bring you off mute and you'll be able to ask your question live. Alternatively, if you have a question, please drop it into the Q&A feature as well at the bottom, and Andreas will answer them through that as well. I think we've got one question so far, Andreas, whilst you were going through, which is from Deliga, which was just asking if you'd say a little bit more about how ocean technologies can better influence marine life in a positive manner. Quite a broad one, but if there's any elements of that you'd like to touch on there.
Well, thanks, Deliga. I appreciate the question. It's kind of become a bit of a trope and a bit of a cliche for us to say we understand more about the moon's surface and Mars than we do about the oceans. But it is actually really true. We don't really understand a lot about the oceans. I said we use the statistics as a magic wand, and I don't mean to denigrate any of our great scientists because they're doing really excellent work. But the reality is we don't understand. And every time we go out, say, to do a biomass assessment survey in an ocean basin, the biomass estimate changes. And sometimes it changes a lot. And that's not a reflection of bad science. It's just a reflection of the fact that we're so data poor. And the systems in the ocean are changing so fast, particularly in the last 20, 30, 50 years. They're changing so quickly that even if you add a good picture of it at any one time, it becomes obsolete really fast, really quickly. And so the need that we have to observe these things is absolutely critical. And the opportunities we have to not only know what's going on, but actually make intelligent decisions about how we manage our marine estate and how we take actions to mitigate to the extent possible that the impacts of climate variability are extremely important. And so, yeah, these observations are really critical. Just to give you another idea from the ocean carbon perspective, we know that CO2 is a big contributor to global warming. This is, we understand this quite well. But the Southern Ocean is a really key to that. It's a really big carbon sink. The carbon cycle in the Southern Ocean is a big contributor to the ocean models. That one mission, that one 196-day circumnavigation of Antarctica, when input into the ocean models, it took us a few years to understand this properly. But when we took that air-sea flux data and put it in the ocean models, the ocean, the global carbon budget, planet Earth changed 5%. That one mission, because there was such little data in a global sense. I mean, we've got Argo floats and SOCOMs and research vessels going back and forth. We didn't have cohesive data set. We're still so data poor. So there's a long way to go before we really try to close the gap. So yes, anything we can do with technology to help close the gap on observations, absolutely critical. And if we can work together in that regard, so much the better.
Perfect. Thanks,
Yeah.
Andreas. Um, Also, thanks, Ruth, there, just for the kind words as well. As I said, if anyone does have any questions, please drop them into the Q&A feature. Alternatively, raise your hand as well, and I can bring you on stage to ask it live. Uh, don't see any questions coming through just yet. In that case, I think Natalie, you said you had a question you'd like to ask.
Yeah, thanks, Andreas. And super interesting. I have actually I've been on a boat in the Southern Ocean, so I do know what it's like to be at sea there. It's pretty intense. And yeah, the photos do not do it justice, that's for sure. I think someone actually flew across the bridge from one end to the other end. I've never seen a human being fly across a room before. So
Yeah.
Um, I was just wondering, so this is really taking place in your area, so in the Southern Ocean and around Australia. Is there any plans to kind of roll out these kinds of observations further afield? So I think most of us tonight are kind of in the Northern Hemisphere and maybe further towards Europe. So is there anything happening around our area in terms of these sort of developments and observations?
Yeah, sure. Good question. So we're big believers in collaboration. We're big believers in working together to help each other enable these important bits of work. And so in North America, we work a lot with both U.S. and Canadian agencies in particular to help support both fishery science and physical oceanography. The learnings that were developed through our work with Saildrone have been adopted by NOAA in their activities both in the Atlantic and North Pacific, and the Chukchi Sea, Bering Strait. And they have a lot. I can't remember how many sail drones they have. They must have something like 20 sail drones now operating in a number of different capacities across the NOAA agency. And so a lot of those learnings are really good. We have longstanding collaborations, particularly with the Pacific Marine Environment Lab at NOAA on ocean carbon measurement. In fact, we just signed a new MOU a few months ago. So we work really close to them on technology sharing and on sharing best practices and methods. That's really important to us. In Canada, we work with can't use the Environment and Climate Change Canada, I think it's called now, and Fisheries and Oceans Canada on the fisheries biomass assessment piece, as well as some air-sea flux and some other things on the Atlantic side. And there's always a conversation about what technology can be ported and how we can share those learnings. But we're always up to doing that, and especially agencies which are progressive and willing to adopt new methods and approaches. And it's really hard on the fisheries piece. Has been really challenging getting partner agencies to say, well, let's move away from nets, let's move away from catching stuff, and let's go to like processing, using the bioacoustics more prominently in our biomass assessment estimates. It can be a very political challenge because some of that work feeds into industry limits on catch and so on, and so there's some challenges navigating there. But we share that work certainly. We tend not to operate outside of our kind of domain because we have such limited resources and we have such a big need in Australia. But we do collaborate with others, and we hope to do more work with other agencies. We don't do a lot with Europe, to be honest, to be fair, although we have had some recent interactions with NOC in the UK and NEOS in the Netherlands, but it's still emerging. So I'm open to conversations about how we can close the loop there for our European colleagues.
Thank you so much.
Thanks, Andreas. Another great answer there. And I think we do also have another hand raised, if I'm right. Yep. We have a hand raised here by Ruth. So Ruth, I'm just going to bring you onto the panel so you can ask your question live. There we go. Ruth, you should be able to unmute yourself now and ask your question.
Yeah, hello guys. I'm Ruth from Ghana, West Africa. With this emerging technologies, I would like to know if they are, should I say, climate-based or weather-based, because in its maintenance and its operation, the weather conditions at the Western side. I mean, Europe is different from that of Africa. So I would like to know if these technologies can equally be used in African seas, or there are some that have been developed to suit the weather conditions in Africa.
Thanks, Ruth. That's a really great question. And that's one of the benefits I guess we do have in Australia with the massive marine estate that we have to contend with, is that we tend to see a little bit of everything. And so there's a slice of the marine world present somewhere in some condition in the Australian domain. And so generally, particularly with the Southern Ocean work, what we say is if it survives there, it can survive anywhere. They're pretty extreme conditions when it comes to operating, particularly at the sea surface. And so without knowing the details, I don't know much about the African continent. I've been involved in some Indian Ocean work on the east side of Africa, but not in the Atlantic sector. But I would say that some of these technologies are probably well placed and well mature to support activities in the Atlantic Ocean. I know the Europeans have used sail drones in the Mediterranean and also to do transatlantic crossings and to do some of the hydrographic coastlines going north-south in the Atlantic. And so I would suggest that those technologies are nearing maturity to be used both coastally in the Atlantic and also offshore.
Oh, okay.
Yes, and they're getting better every day. So there's always yeah.
Okay, thank you.
Yeah. No, thanks for the question.
You're welcome.
Perfect. Thanks, Andreas. And we do have another couple of questions here via the Q&A feature. So if I just read them out. So first we have here from Amy, who says that you've spoken about increasing collaborations quite a lot, mentioned that conferences like Oceans are a venue for this. Are there particular sessions types that you would like to see more of at conferences to help boost collaboration?
Yeah, thanks, Amy. That's a great question. I think there's probably two things that I'd like to see more at Oceans, and I will preface this that I've been absent from the Ocean circuit since before COVID, and so there's a little bit of a time warp happening in the last few years. I haven't been to one, but there's two areas that I've always felt could be improved. The first is talking about failure. This can be a touchy subject with a lot of people. And I'll give an example of one community which I've been involved with, which is the buoy workshop, which is a workshop that happens every 2 years, happens to be run by MTS, but really focused on oceanographic mooring design and engineering. And it's a very small community, maybe 50 people or 100 people at this kind of workshop. But what's really effective about it is we all go in there with this thing of like, we want to learn from each other's mistakes. And most of the presentations and most of the conversations are around, we tried this and it didn't work for these reasons. What I struggle with at some of the ocean science conferences and sometimes at Oceans is that we see these presentations and they're all given as if everything went great. We had an idea, we built a thing and we used it, and oh, look, it was wonderful. And I'd like to see if we can find a way to get the community to talk a little bit more about their failures, because that's how we learn and share information with each other. So somebody who comes up and says, hey, look, we had an idea for something, we built it, we tried it, and it didn't work. And it didn't work for all these reasons. And these are the problems that we had, and these are the problems that we solved, and these are the problems we couldn't figure out. Because that's how you generate learning, and that's how you generate conversation. And particularly with engineers who are natural problem solvers, you start throwing problems at them and they'll start engaging with each other really quickly, because everyone will have 100 ideas and they'll be able to have a conversation. And so how do we kind of break that little cultural taboo about, like, let's talk a little bit about failures? And so maybe we need to have a session that's perhaps prompted or curated to say, hey, look, this is a specific session to say, tell us what didn't work. Let's talk about our failures and what we can learn from them. The other thing is that we quite often get caught up, again, being engineers, talking about solutions. And so we go to these conferences and we have these topics headings like acoustic technology, and everyone comes in and talks about their solution to a particular problem or a particular subset of a problem. What we don't talk about at Oceans is what are the problems to begin with? What are the challenges? what are we facing? What is the spectrum of issues that we need as a community to address, and how can we work on those? What are the big picture? What's the big picture issues that we need to talk about? I talked a little bit about trends earlier and some of the challenges in the Southern Ocean, but it'd be great if we could find a way to have like a workshop or a roundtable or something where we can talk a little bit about the problems, and we can, as a community, see if we can address them. And so I alluded to one earlier, which is, can we figure out naming schemes? Can we come up with common lexicons? And IEEE is a great place to do this, to come up with standards and approaches for things. But the second thing is, can we agree on interfaces? Can we agree on API calls? Can we agree on interoperability? Can we talk about some of these high-level challenges that prevent collaboration from happening? And can we, from a technical level, break them down and help streamline some of the activities we're doing? So having that discussion about problems, not just the solutions, which are really cool, and we love the tech and so on, but having questions about the problems and seeing if we can learn through that process. So that's just one idea, but those are the two things I think in the past that have stuck out with me at Oceans that I thought maybe we can find a way to kind of fix that. Sorry for rambling on, but thanks, Amy. That's a good question.
Definitely not rambling on there, Andreas. Definitely not. It's good to get the detail. And then we've got one final question at the moment, which is from Anonymous. So, do these autonomous vehicles can carry out to monitor the species diversity at different strata without conventional methods of deploying nets other than using eDNA?
So yes and no. So if you're talking, say we're talking about the fisheries problem, and you're trying to understand what a particular fishery is doing, if you have a very homogeneous fishery, the answer is yes, you can do it. So for example, in the Chukchi and Bering Strait, if you go and see a fish school, it's probably pollock. It's 99, it's probably pollock. It's very homogeneous. So you don't have this mixed species happening. But in other parts of the world, you have mixed species. And when you have mixed species, then differentiating them becomes difficult. And so you need to do more calibration, you need to do more signal target studies to kind of disentangle them. And in those situations, yeah, you probably still need to have nets to get the species mix that you're looking at. And so the answer is not solved. I don't want to make it seem like we figured this out completely, but I think we've gotten far enough along that we can operationalize a lot of these approaches and build on them. And so in fact, I do think that I think it's the Alaska, I think it's either the Alaska fishery at NOAA or the Pacific Fishery Lab, I can't remember which one, is actually trialing now in situ, along with the McKenna net tows, for pollock species and to set the catch limits, and for the pollock species biomass assessment, doing that in situ with sail drones, and having a conversation about transitioning those observations and the model data inputs from the conventional net catches to the automated processes. And again, one of the reasons they can do that is because they have this very homogeneous fishery that's pretty consistent, and so that enables that sort of to happen a lot easier. But I still think they're probably years away. I don't know if there's anyone here from NOAA who can tell us otherwise.
I was going to say, if there is, please feel free to raise your hand.
Happy to be corrected.
But no, great answer again, Andreas. And I don't see any more hands up at the moment, and I don't see any other questions in Q&A. So I'll just give it another couple of seconds if anyone wants a last chance to raise a hand. Nope, and no final questions in Q&A. Okay, in that case, just want to say a massive thank you to Andreas. I'm sure everyone else here would want to say a big thank you as well. So very much appreciated. Thank you to all who've attended another one of our ECOP webinars. It's very much great to see you all in attendance as always. And if you do have any follow-up questions or anything else you may think of after the fact, feel free to email us. I can pass on the questions to Andreas to get back to you as well, which I'm sure he'd be happy to answer. But yeah, thank you very much, everyone. Hope you all have a great morning, lunchtime, evening, wherever you may be, and hopefully see you again soon.
Thanks all.